my screen, and we are going to welcome our second guest, whose name is Professor Xia Zhijia. And Professor Xia Zhijia now is a full professor at School of Computer Science and Engineering, and at the Central South University. He received his bachelor and master degree from Zhejiang University and PhD from NTU. And he's doing a lot of stuff in the visualization and computer graphics. And he won the Best Paper Award of the CDCG, and also the best paper honorable mention in attribute visualizations in High 2025. And he also served lots of PC and chairs for the top tier conference as well. Okay, I'm going to move this to the Professor Xia. I saw this Professor Xia has come in, so I already introduced you. So please start. Thank you.
Thank you, Professor Pang. Let me share my slides. Okay, is everything okay?
Yes, everything's good.
Okay, thank you. Good evening, everyone. I'm Xia Jiazhi from Central South University. Today, I would like to talk about parametric nonlinear dimensionality reduction for high-dimensional data visualization. For this topic, we have studied for many years. And high dimensionality is a critical feature of big data. The ubiquitous sensors generate large volume high-dimensional data every day. High-dimensional data visualization is a powerful tool. Here, there are several typical visual analysis interfaces for labeling data and improving the data quality. In these interfaces, high-dimensional data visualization provides a space to perceive and interact with high-dimensional data. There are many types of visual representations for high-dimensional data, such as line-based parallel coordinates, pixel-based heat map, and glyphs, such as star coordinates. Among them, the most popular one is the skate plot. And dimensionality reduction approaches are proposed to embed data from high-dimensional space into a 2D space. In the skate plots, the distance between points indicate their similarity. Therefore, the cluster patterns and outliers can be visually detected. In skate plots-based visualization, the performance of dimensionality reduction approach is critical. It's also a core topic in machine learning. Many famous researchers have devoted to dimensionality reduction. Formally, dimensionality reduction is to find a proper function that map the high-dimensional data into low-dimensional space. For linear approaches, such as PCA, the function is explicitly represented as a transformation matrix. For nonlinear approaches, such as TSNE, and UMAP. There isn't an explicit function for the dimensionality reduction. The function is represented in a pointwise manner. However, the nonlinear approaches are more popular in visual cluster analysis tasks due to its performance in capturing nonlinear features. There are several challenges for the implicit dimensionality reduction function. First, they cannot be updated once computed. It don't support effective interaction. The dimensionality reduction function is coupling with the projected dataset. Adding a new data point requires to generate a whole new function. And the function cannot be reused and shared. So when we think about this question, we propose a possible solution, try to provide the parametric approaches. Neural networks can propose an explicit representation for nonlinear function. We can learn their function. With the explicit dimensionality reduction function, new data can be projected without recomputing the whole function. Also, the dimensionality reduction function can be updated with incremental learning. But a high-quality mathematics and parametric dimensionality approach is challenging. Many researchers have explored to learn an embedding, such as a parametric version of TSNE and UMAP, and use the contrasting learning. But the embedding qualities of them are lower than the non-parametric version. We can look at the embedding results. The left are the non-parametric approaches, including TSNE and UMAP. In the right are the existing parametric approaches. We can see that the embedding quality is obviously lower than the non-parametric approaches. So we wonder, can we train or learn a parametric version of a high quality embedding? So we look at the existing embedding approaches. We have an observation. When we look at this, we would like to ask a question. What is the key for a successful dimensionality reduction approach? First, all dimensionality approaches aim to preserve the critical information in the no-dimensional space. The second, due to the intrinsic difference between the high-dimensional space and the low-dimensional space, it's impossible to embed high-dimensional structure into no-dimensional space without any loss. Let's look at the three approaches. The first one is isomap. It tries to preserve the geodesic distance among all points. Similarly, the autoencoder tries to preserve the Euclidean space, distance, and variances. In another word, they try to preserve all information of the dataset. We know that it's impossible because the intrinsic difference between the high-dimensional space and the low-dimensional space. The third one is the famous TSNE. It tries to preserve the local probability density distribution. It gives up the hard constraint of rigid high-dimensional structure. Instead, the local probability density distribution is a soft constraint. As a result, TSNE usually achieves better cluster patterns, especially in non-linear dataset. So we learned that we need to decrease the amount of preserving information and achieve more higher quality embedding. Based on these observations, we propose a contrastive learning-based parametric dimensionality reduction approach. As far as I know, this is the first parametric approach that achieves comparable and even superior performance with non-parametric approaches such as TSNE and UMAP. In the dimensionality reduction approaches, false neighbors are the major issues of embedding quality. In typical approaches such as TSE and UMAP, there are two main stages can cause false neighbors. First, in the hand-dimensional space, when we construct the k-nearest neighbors, there will be false neighbors due to improper metrics or improper k-values. Second, in the embedding process, false neighbors may occur by the embedding algorithm. Contrastive learning is a self-supervised representation learning method. It pulls similar instances together and pushes dissimilar instances away to learn an effective embedding. The similar and dissimilar relationships are represented by positive pairs and negative pairs, respectively. More importantly, for each instance, usually not one positive pair is needed. For contrast, construct the positive pair of each point. We sample one point from its nearest neighbors based on similarity. We note that the point with high similarity has more possibility to be a true neighbor and also has more possibility to be sampled. Compared to take all k-nearest neighbors as a constraint of embeddings, our method has a lower possibility to include false neighbors. And for the negative neighbors, all data except itself and its positive counterparts are considered as negatives. We randomly sample several ones from them. Let's look at the pipeline of our approach. The left is a sampling strategy. The embedding function is learned by a neural network. And the network is trained with a contrastive loss. After that, the user can interact adding mask links and cannot links to steer the embedding results. It's also an advantage of parametric approaches. The embedding function represented by the neural network can be updated in the learning framework. Compared to the cross entropy loss, anti-accent has an increased penalty with high similarity. Therefore, we choose it for our loss function. Now, we can preserve the neighborhood structures with high quality. However, the two clusters may still be close to each other. We want to further improve the visual separation among clusters. The gradient curve of NT accent shows that the lowest similar negative pairs have a minimal impact on the model update. However, the 2 points of such a negative pair usually belong to different clusters. So our intuition is that if we can increase their contribution to a model update, we will be able to extend the distance between different clusters in the embedding space. Now the questions are, which negative pairs to increase the gradient and how to increase the gradients? Uh, we can select negative pairs by similarity, but the range of similarity should be well considered. After a statistic analysis, we choose the one with similarity less than 0.1. The next question is how to increase the gradient. The anti-accent shows that um, an exponential gradient curve works well in separating dissimilar data. We would like to add a similar but smaller continuous distribution to the gradient in the low band of the similarity to separate clusters. Therefore, we choose a positive skewed distribution, which is similar to exponential distribution. We're adding it to a gradient curve of an anti-accent. And finally, we get the redefined gradient curve of negative pairs. Thus, we can achieve a clear visual cluster patterns. Uh, what's more, here is the interesting part of our approach. In the non-parametric approaches, users cannot interact with the embedding. Even if they noted wrong embedding results, they cannot correct it. The learning-based framework and the positive and negative pairs-based contrasting constraints gives us an opportunity to elegantly incorporate pair-based interaction into our embedding framework. Users can specify the must link and cannot link to steer the cluster, which are very popular in interactive cluster analysis. When a must link is specified, a positive pair is set with probability 1. For a cannot link, a positive pair is set with probability 0. Here we look at the example. This is an embedding result of an animal dataset. In the upper left corner, there are 2 clusters. We found that the 2 clusters are both butterflies. Consider other clusters are cats, dogs, horses. We think the 2 clusters should be merged into one. Therefore, we set a mask link to steer the embedding. After the mask link and quick update, the new embedding presents the expected pattern. Here are more results of our approach. Compared with other approaches, our approach presents better visual class separation without inaction. Uh, in the right um, bottom corner is a result of our method. And there are the result of our other methods such as UMAP, uh, TSNE, and other methods. Our embedding also outperforms other approaches in major quality metrics such as uh, continuity, trustworthiness, KM-based accuracy, DSC, and so on. In terms of trustworthiness, our approach works better than other methods. In continuity, our approach doesn't achieve superior performance. The reason is that the metric treats false neighbors as the true neighbors. Therefore, it's not a reliable metric. The results on can classify accuracy and the neighborhood hit also demonstrate that our approach has achieved better quality than existing methods. In terms of visual cluster separation, the results show that our approach outperforms all other techniques. The aberration experiments also verify the effectiveness of the anti-accent loss and the gradient rate definition technique. With the high-quality parametric approaches, we can unlock many research directions. First, the learned explicit embedding function can be directly used to embed out of sample data. Naturally, we would like to try streaming data visualization based on the parametric embedding approach. Another interesting direction is cooperative visualization. The explicit embedding can be reused and shared. It can provide a shared visual analysis space for distributed high-dimensional data sets. Next, let's talk about the streaming dimensionality reduction. Our paper on in the Waste 2023 explored the streaming data visualization based on our parametric dimensionality reduction. And the streaming data visualization is a common task in visual analytics. However, the current dimensionality reduction methods don't support reuse and local update. Their computation is also time-consuming. Handling high-speed and time-varying streaming data is a challenge. Our parametric dimensionality reduction provides an opportunity. However, it's still non-trivial. First, the embedding algorithm should be conducted in high speed and adapted to the time-varying patterns. Second, the mental map should be preserved during the temporal analysis. In other words, the embedding should be stable in some extent. To track this challenge, first, we present a parallel framework to resolve the dependence among different parts and introduce efficient calculation strategies to enhance the processing speed. Second, we introduce an incremental learning method designed for parametric dimensionality reduction techniques to accommodate changes in data patterns. Thirdly, we propose a visual feature-based adaptive stability constraint into the updating process, ensuring the stability of the embedding results. We divide the computational embedding into three modules. It includes the new data embedding modules, the embedding function updating module, and the embedding updating module. Ideally, we would like to run them in parallel for high-speed computation. In a traditional framework, the three modules are computed in a serial way. They're dependent on each other. For example, when new data points come in streaming, the embedding and the embedding function need to update in time. The new coming data should also be embedded with the updated embedding function. The embedding should be updated based on the updated function and the embedded new data. So the key of the parallel framework is to resolve the dependence among them. With our parametric dimensionality reduction approach, we can embed the new data points with the explicit embedding function. Note that if there is no large change in the embedding function, we can use current embedding function without frequent updating. Similarly, because compute a new embedding function is time-consuming for streaming data analysis, we detect whether global pattern change is happened. If not, we only update the embedding locally without updating the embedding function. Third, updating the embedding is also time-consuming. We cannot afford the time cost to recompute the embedding of all data points when each new data point comes. Therefore, we only embed the new data points and merge them with current embedding. Specifically, the embedding of new data in time step t is merged with updated embedding in time step t-1 as an updated embedding in time t. This strategy slightly sacrifices the embedding quality, but significantly improve the efficiency. With this strategy, the three modules are computed in parallel without a dependence on each other. The embedding function updating is most time-consuming, therefore its frequency is the lowest. The embedding updating and the new data embedding are frequently conducted to deal with streaming data. The new data embedding is based on our parametric dimensionality reduction. It has the advantage to embed the new data without recompute the embedding function. And the learning-based embedding has another advantage. We can introduce incremental learning for its online update. We propose a similarity-based constraint to ensure the embedding quality, a perception-based constraint to ensure the stability, and adaptive updating strategy to balance between the two constraints. In the quality constraint, we design two loss items, the learning loss and the preservation loss, to guarantee the embedding quality of new data and existing data. As for the stability, due to the inherent randomness of algorithms during the updating process, sudden change can happen during the embedding updating. The mental map is not preserved. To solve this issue, we proposed stability constraint to preserve visual features of the embeddings. These features are the relative position, distances, shapes, and the size of visual clusters. There is a trade-off between the embedding quality and the stability. To get a good balance, we introduce an adaptive stability weight to update embeddings when data patterns change and keep embeddings otherwise. Here are the embedding results of three different strategies. The first one is without updating the embedding function. It cannot capture the variant patterns. The second one is with quality constraints only. In each time step, the embedding quality is high. However, the visual consistency among the time steps are missing. The third one is our adaptive loss. The embeddings have both high quality and consistency. And for the embedding updating, the data pattern changes in streaming data mainly occur locally. The recomputation of the embedding for all data is often unnecessary. Therefore, we introduce a hybrid embedding updating strategy. We employ a k-nearest neighbor-based detection algorithm to detect changes. In case of local structure changes, we update the embedding locally without updating the whole embedding. When global pattern changes are detected, we use the updating embedding function to then compute embeddings for all data. Finally, we select 4 SOTA streaming dimensionality techniques. 2 of them are linear methods, and the other 2 are nonlinear methods. And we also choose 5 real-world datasets to conduct experiments. Regarding to the runtime performance, our approach demonstrated the most impressive overall results. The streaming PCA expect higher throughput output on the lower dimension datasets. However, its performance declined as the dimensionality increased. In contrast, our approach consistently performed well across different data dimensionalities. In terms of embedding quality, our approach performs the best in preserving local structures compared to other methods. And during the streaming process, our approach is the most stable. As for the embedding stability, our approach consistently presents lower levels of embedding changes compared to the existing methods. our method is also the most stable one. In the embedding results of different time steps, our approach presents the clearest uh, cluster patterns and stability. Uh, the first four are the existing methods. Here we look at the video of the streaming analysis process. You can see that our proposed method is quite stable and present clear visual cluster patterns. Next, we would like to discuss how parametric dimensionality reduction can be used in cooperative visualization. In a scenario of security-aware cooperative visual analysis, the data are distributed in many, in many analyses. They want to compare the data of each other, but without sharing the raw data. The question is how to produce a global embedding without sharing raw data. There are a few research efforts in this direction. A paper from Jiazhi proposes a solution. However, it must share a part of data and the resulting security risks. In addition, the embedding results have large distortions, so it cannot be used in real applications. We have studied this topic for several years. The first solution is to adopt federated learning. However, we have not seriously worked on it because there are two issues. The first one, we need a high-quality parametric nonlinear dimensionality reduction approach. When we start to think about this topic, we have not developed the contrastive learning-based approach. Therefore, we hold on this idea at that time. The second reason is a non-IID issue. The quality requirements of joint embedding is higher than classification models. In comparison to classification accuracy, embedding has more strict quality metrics. The second solution we consider is the security multi-party computation. The SMPC designed blind computation technique for multiply operation. However, it does not support the critical computation of TSNE. It cannot get a result with masks. To address this issue, we design new blind computation for division operation of power operations. As a result, we achieve high-quality joint embeddings with SMPC. The analysts do not need to share their raw data. However, the SMPC is quite slow for real applications. The federated learning-based solution is still appealing. Let's have a short conclusion of this talk. We have discussed the importance of parametric nonlinear dimensionality reduction. We propose a contrastive learning-based approach with a superior performance. The high-quality parametric dimensionality reduction approaches support reusing, sharing, and local updating, thus opening more research opportunities. That's all. Thank you.
Uh, okay, thank you very much, Professor Xia, for amazing talk. And I have a question. So even though I'm not an expert in the area of the visualization, I just want to curious to ask, how do you think like the AI will changing the way of the visualization comparing to previously, like we do some computer graphic or CV way of doing some like image visualization things?
Thank you, Professor Pan. It's a quite interesting and important question. Uh, Nowadays, the generative AI has changed the state of many research areas, uh, also includes our visualization. We know that visualization also need quite a long time to design, develop, and update uh, the visualization tools. Uh, Usually, it takes a half a year or 1 year to um, finally develop a visualization tool. Uh, and many different characters, such as the designers, uh, the domain experts, the developers, and the users have participated in this process. Uh, Different knowledges and skills are required. Uh, and with the generative AI, it's a recent research trend. Uh, uh, I see that many generative AI tools have been introduced into different stages of the uh, to design and develop the visualization tools. For example, it can conclude the design requirements of the users from the interview records. We can use large language models to conclude the design requirements and transform them into a structured form. Uh, in this form, the information can be directly used by the design models. And also, we can use the generative AI to automatically generate the visualization design, for example, the visual representations, uh, or to generate the codes for the visualizations. Uh, Another possibility is that we can use the generative AI to mimic the people's or align with people's uh, perception. We know that the uh, golden metric of how good a visualization is based on the human's visual perception. In the past decades, we perform and conduct many user studies to explore the visual perception. With the generative AI tools, I see many explorations to use the large model to align with people's visual perception. Maybe we can uh, build uh, an end-to-end to-end visualization generation pipeline. Uh, that's my considerations. Thank you.
Okay, thank you very much. This is very detailed explanations. And I was like to ask is if there were anyone else have a questions or comments to this webinar. Anyone wants to comment on this? If no, and I would like to thank two of our top, speakers, um, like Professor Kanamori and Professor Xia. And I think that's pretty much it for today. Thank you very much, and good evening and goodbye.
Thank you. Goodbye.